Okay, and now we are officially recording. So, good morning, my friends. Today's lesson is about changing back and forth between bases and also about writing numbers in Roman numerals. Let's start by talking about what it would be like to look at a number that's in a base other than our own. Try to remember that once we had talked about numbers in base 10, we assumed that this was the ones place, tens place, hundreds place, and thousands place. If this number was in base 10, we'd assume there were 3 ones, 0 tens, 1 100, and 2 thousands. Notice that those numbers 1, 10, 100, 1,000, they're all powers of 10. So for a question like this, we're going to instead employ the powers of 4. And it might help you to hold on a minute and take a look at what the powers of 4 are, so you have a little bit of a grasp on what kind of numbers we're talking about here. Let's take a look right now at what the powers of 4 are and discuss that for a minute. And I'm going to kind of put it on the side here. But while we're studying, we have this as a little bit of a quick reference. All right. I have, of course, 4 to the 0. Like anything to the 0 is 1. And then I also know that 4 to the 1, of course, is 4. Bigger numbers, 4 squared, 16. 4 cubed is going to be 64. Okay. These small power facts, these are called power facts, kind of like how you have times tables facts. These are called power facts because they are the powers. You could also call this a power table. The same way you have a times table, this is a power table. So we have the powers of 4 here, 1, 4, 16, and 64. So instead of thinking about this number like there are 3 ones, 0 tens, and then this is hundreds and this is thousands, instead this is still ones, but then what's going to happen is this is going to now be 4s. And this is going to be the next power, 16s. And this is going to be the next power, 64. So if you want to try to visualize what this might look like, you can interpret it to be, this is the 1, this is the 4, and it's like a stick. This is 4 groups of 4, which would represent 16. And this is 4 layers of 16, which represents the 64. And if you look across the top, they did include these digits 2, 1, 0, and 3. So we have 2, 1, 0, and 3. So what does the 2 represent? The 2 represents the number of 64s. And what does, and what does the 1 represent? It represents the number of 16s, and so on. So let's see if we can come up with a solution now for what this number actually really would be. It's 2103 base 4. All right, I encourage you guys to now change your view from speaker view into gallery view. And if you do that, or rather from gallery view into speaker view, and if you do that, you get a nice broad vision here of my writing, and you'll be able to see what I'm doing. If you have it in gallery view, you'll see everybody, which is not a bad thing, but it'll be hard for you to see what I'm writing here. And I'd like it if we could all look together, please, at my video that I'm showing so that you could see how to do this. I have maybe 5 or 6 examples that are like this, and then a couple of examples that are in the reverse direction. And I need for us to be comfortable with this. This is really very easy to do. This is not hard work. It's just multiplication and calculator stuff. I begin by considering the powers of 4. What are the powers of 4? Well, like I said earlier, I have 4 to the 0 is 1. 4 to the 1 is 4. 4 to the 2 will be 16. 4 cubed is 64. And I'm going to stop there because I have the 0, 1, 2, 3. This is for 4 to the 0. That's for 4 to the 1. That's for 4 squared. And that's for 4 cubed, right? Okay. So now that we've got all that in place, I can take this idea right here and say I need to find 2 times 4 cubed. For this one, I need to find 1 times 4 squared. For this one, I'm going to try to figure out 0 times 4 to the 1, and then I'm going to do 3 times 4 to the 0. I have a reference here of what all the powers of 4 are. Here's a power table. So this has now become 2 times 64. At this point, it's all old arithmetic, and you know what to do from here. I want you to try to remember, and this is something that is really very easy to remember, but anything to the 0 always equals 1, and that's really very important. Don't forget that. Anything to the 0 will always be 1. Now, you can use a calculator for this part, or maybe you could do it in your mind, and if you could do it in your mind, 2 times 64 is 128, 1 times 16 is 16, 0 times 4 is 0, 3 times 1 makes 3. Add them all up. You get 147. So this is how you're going to convert a number that's in an alternative base into a decimal number or a number that is in base 10. You're going to look at each of the different places and use the base and find the powers of the base. So we have a 0 place, a 1, a 2, a 3. So it's going to be 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3. Before you dare to try to put this together, you must contemplate the power table of 4, because you need all of these numbers as part of the story of how to calculate this. All right? Okay. So let's do a couple more cases of this. Let's see what else we have in our PowerPoint. I'd like to finish the PowerPoint before I jump into the examples. So let's come back to our PowerPoint now. Okay. So when you say a question like, well, what does that 2 represent? Well, the 2 represents the number of 64s. In the same way the 2 would have represented the number of thousands, because that's 10 cubed, it represents the number of 64s, because that's 4 cubed. Let's talk now about some other bases. Let's talk about base 5. Write a short answer for each as one of the essays for your next exam. So for part 1 and part 2, what that means is get comfortable with the way this works so that when you take your exam, you're able to answer questions. Okay. What are the place values in base 5? What digits are needed? How would 38 be expressed in base 5? Write the first 15 counting numbers in base 5. So let's do these questions a little bit out of order. I'm going to talk about how to write 38 in base 5 last. First, I'm going to talk about what are the place values in base 5. And this is going to always be the easiest thing to answer. What are the place values in base 5? Well, the place values are going to be, of course, the powers of 5. So what are the place values of 5? Place values are usually 1, 10, 100, 1,000. What are the place values in base 5? Well, there's 5 to the O, that's 1. There's 5 to the 1, that's 5. There's 5 squared, it's 25. 5 cubed is 125. 5 to the 4th is 625, and so on. This is what we were expecting for you to answer with what are the place values in base 5. What digits are needed is a little bit of a different question now. What digits are needed? Well, these are the place values, 1s, 5s, 25s, 125s, so these are place values. When you see place values, I want you to try to think about the 1s place, the 10s place, the 100s place. What are those numbers, 1, 10, and 100? They're powers of 10. So in base 5, the place values are powers of 5. 1, 5, 25, and so on. What are the digits? The digits are going to always be all of the numbers starting from 0 up to, but not including the base itself. So for base 5, it's going to be these. Notice there are 5 digits. Notice that 5 is not a part of it. So for base 5, I'm going to make 2 important notes here. Number 1, there are 5 digits. Number 2, 5 is not one of them. Can we remember that? Okay? So like, for example, while we're in this conversation, let's also talk about, how about the digits for the place value of 9? What are the digits for place value 9? Well, it would be, there's 9 of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, not including 9, right? So there are 9 of them. And also, 9 is not one of them. Okay, so when you're asked to tell what the digits are in a certain base, Count from 0 up to the base, but don't include the base. And there are supposed to be that many digits. Further, the number itself that is the base is not one of the digits. So we can remember those little hints will always help us. That will be true for every number system, whatever the base is, that will always be true. I do see a question here that was asked, how far do you want us to go with the place values? Remember, we're going to have multiple choice questions that are associated with this. And if you see something that's a short answer or essay or anything like that, I would say just give the first couple of them until they start to get a little ridiculous. Like 625 is pretty extra. The next one after it is going to be really very big. I'm going to leave that to your discretion. As long as you really give the first 3 or 4 of them, you're going to get your credit for that. All right. We also were asked when we were looking at this question a couple of other little details. For example, they're saying, yeah, also, write the first 15 counting numbers in base 5. Okay, so if you want to write the first 15 counting numbers in base 5, you know, we have to kind of go from the very beginning. So let's begin with the first 15 counting numbers in base 5, and what would that look like? Okay, so if you're in base 5, the first 15 counting numbers, well, the first couple of numbers are going to be pretty straightforward and easy. Okay, it's going to be 1, 2, 3, 4. And we'd like to write a little 5 down here to say, and by the way, this is 2 base 5. Right? But now I can't write 5. Okay, so what am I going to do? Well, I can't write 5. So what I'll do is the next best thing, and now this is single digit, right? This is single digit. Let's do a double digit number now. A double digit. The first double digit number I could possibly do is 10. And what does the first number mean? Well, this means that this is the ones place, and this is the fives place. I'm sorry, guys. The camera's kind of acting up. You could see it's getting blurry. I'm trying to make it that it doesn't blur. But what happens is we can't write 5, right? We already discussed that 5 is not a digit here, okay? And notice that they asked for the counting numbers, so 0 is not qualifying as a counting number. We'll start with 1. But the next number after 4 looks like 10, because the next number after 9 is going to be, okay, we return to 0. So what are the digits? 1, 2, 3, 4. What comes next? 0 comes next, and we bump this up 1. So this right here is the same as our favorite number 5. If I write this, now you're at 6. The idea is it's 1, 5 plus 0 ones, that's 5. Now you have 1, 5 plus 1, 1, that's 6. If I have 1, 5 plus 2 ones, now you're looking at 7. 1, 5 plus 3 ones, now you have your 8. And then, of course, 1, 5, and 4 ones. And now you have the 9. So before we carry on, do you see how when we get to the end and we've exhausted every digit, that's what we have to do, is we have to kind of go ahead and bump up. So what do we do to get the next number 10?
Wouldn't we have the first number be 20 in base 5?
That's just it. You got it. That's exactly it. So we're still in double digits, and since we cannot say 1, 5 now, we're going to have to bump this one up to 2. So now I'm looking at 2, 0. It looks a little bit like 20, but it's not 20. It's 2, 0, meaning there are 2 5s and 0 1s, and that's 10. Okay? How do you get 11? 21, right? Or 2, 1? We're trying to say, can you please give me 2 5s and 1 1? That's 11. And then 2 5s and 2 1s will be your 12. 2 5s and 3 1s is 13. 2 5s and 4 1s is 14. And we got to go one more, right? Because didn't they ask you for the first 15 numbers, right? So I'm going to have to bump up one more time. You might feel tempted to write 2, 5, but why can't you write 2, 5? Because
you're in base 5.
because you're in base 5. You got it. That's just right. And base 5,
So what you do 3501.
you're close. It'd be 3, 0.
Oh, but I thought we don't call it 0, so you would call it 3 5s and 0 1s.
Oh, yes, exactly. That's just right. It would be, this represents 3 5s. That's a 5s place. And no 1s. So yes, it's 3 5s and 0 1s. And that makes it the 15 that we need. Okay.
Ah.
So it makes sense, doesn't it? It's really not that hard. And if you take a minute and try to count through in an alternative base, it starts to become clear the whole general idea. And it kind of reminds you a little bit about what it's like to count in our decimal system. When you get to 19, the next thing is 20 because there's not another digit to add to make it look like the next number. So you bump up the 1 into a 2, make it a 20, and make it come back to 0 there. So this is how you count, my friends, in base 5. And if you're comfortable with counting in base 5, then you should be comfortable counting in any base. And now, since we've established that and we feel good about that, let's tackle this other difficult question. What will we do to try to figure out 38 in base 5? Right? Is that what they want?
Yeah.
I have
No.
a quick question.
Oh, wait, this is not in base 5. They want 38 in the decimal in base 5.
Oh.
And we're going to find that in a minute. Now, there's a question I heard. Go ahead. What's your question?
So, do
Let's come back to
bases
this.
have to be like, can they be like anything higher than 9? So can it be like base 14 or something like that, or is it just like?
That's a very good question. The answer to your question is yes. And we're going to study one today that's called hexadecimal, which is the 16 base. It's called hexadecimal. And if you remember your roots, you know hexa means 6, right?
Mm-hmm.
And decimal means 10. So 6 plus 10 makes your 16. And what happens is they use letters for digits. Is probably what you're wondering. They're going to use letters for digits. So like if it's hexadecimal and you're in base 16, right? So after 9, you have a 10 digit and they call it capital A. And then capital B and capital C like that. And we're going to do 3 or 4 examples today with hexadecimal because it's in your textbook and I want you to be familiar with it. The good news is I do see it in your web assign. So it is part of our curriculum and you are supposed to study it. I was thinking, I don't want to give you more than you're supposed to study according to our class, but it is in our textbook and it is in our web assign. So we'll go over that too. So yes, you can have bases as large as 50, 100, a million if you want. It's just a matter of coming up with new symbols to represent your digits other than the Hindu Arabic artistic figures we have here to represent our digits. And the reason why we have alternative bases, by the way, because you probably think of why do we even have it? Well, there's a couple of reasons. One of the main reasons that we have alternative bases and that they're practical and used today is because when we began with the exploration of technology and computers in the 1980s and 1970s, they were limited with what you see as a microchip, which is a tiny thing that has a million little grooves in it that means a lot. That would take up the size of a factory with big vacuum rooms that were either on or off, and everything is either just on or off, which is the idea of binary, 1 and 0. So starting with the idea of 1 and 0 and writing numbers in an alternative format than we're used to because we have 10 fingers, writing it as on and off only, like 1 or nothing every time, the computers are able to calculate and use that. So we had to get quickly comfortable with binary numbers. And then the powers of 2, like 4 and 6 and 8 and 16, also became very crucial and important in building computers and furthering our advancement in technology. So, we have binary, and then we have base 4, which we explored a little bit, but then base 8 is really a very important base too. It's called octal, and oct, like an octopus, 8. Octagon, right? And then we have hexadecimal, which is again a power above again on top of 8. 2 to the 4th now is 16. So some of the most important alternative bases that we study in general are those specific bases: binary, 4, octal for 8, and hexadecimal for 16. You might think yourself 16, why? Well, because of the nature of the science of trying to build data storage, either on or off, and then squared and cubed into the 4th, and now you're at hexadecimal. So that's where it all really kind of comes from. The other important the other important branch of mathematics that it touches on is cultural mathematics. And we're going to talk a lot about different cultures. Actually, in this class, I don't think they go that far with it. Do we? I think we do Chinese numbers. I can't remember off the top of my head, but I think we will be doing alternative. If anything, we're going to visit ancient Rome and do some Roman numerals today. I think there are other examples, though, in your chapter where they show you how to do Mayan numbers and other kinds of numbers. But the point is, anyway, if you were an archaeologist or a historian, you would want to know how they counted back in those days or in different ancient times. And they have different numeration systems with different symbols than the Hindu Arabic that we use altogether. And there are classes where you could learn just how to rewrite. It's a kind of a language class, really, to learn how to write in Mayan and in Babylonian and in cuneiform and in Egyptian and Chinese and in Greek and Roman numerals. And like, in other words, there's a lot of material out there about writing numbers in different cultures. And different cultures don't count the same way we do. They count in different ways as well. So to answer your question, when will we ever need it? It's primarily because of our modern world. In a microchip, you don't see it, but there's a lot of binary hexadecimal stuff happening in those microchips, and that's why we're studying it today. Why are you teaching it to the lower grades? You're teaching it to the lower grades because it will help students understand our number system, which is a decimal number system based on 10 because we have 10 fingers, and it'll give them a more broad scope of how numbers work and how place value works. And that's the reason why we try to include that in that way. Okay, so I hope that helps a little bit. Let's talk now about how we would write. I'm trying to share my other screen. I'm sorry. Let me see. Let's talk about now how we would write this number 38 in base 5. And if you remember how we did base 5 before, I'm so sorry, my friends, excuse me. What I was trying to say is we're trying to go in the opposite direction now. So it's not like I have a number and I know the base and I'm going to use the powers to try to add up and get the base. I have a number that's in our base. 38 is in base 10. It's our number. We know this is 38, okay? And I want to rewrite it in base 5. So here's what I need to do to rewrite it in base 5. And this is not really very challenging at all if you pay close attention and you're familiar with how to divide, okay? Let's start by considering what are the bases of 5, okay, the powers of 5. So I want a 5 power table. All right, the 5 power table says 5 to the O is 1, 5 to the 1 is 5, 5 squared makes 25, and 5 cubed makes 125. Now, do I need this one? No, because 38 is lesser than this one, so I'm only going to use these 3. I'm going to stop there for a minute. Does it make sense that only these 3 are going to be my places? For example, if I was talking about the number 195, would I need the thousands place for that? No, I don't, right? Because 1,000 is larger than the number. Same way here, 125 is larger than this number. So I'm not going to consider this. I'm only going to be using these 3. And what that tells me is that my solution is ultimately going to look kind of like this. Meaning it will have 3 digits, base 5, and it will be equivalent to 38. So here's how we handle it. We're going to take 38, and we're going to continually divide by all of the powers of 5 until we've reached nothing left, okay? Let me get a fresh paper to make it really clear. 38 in base 5, base 5. Using 5 to the O is 1, 5 to the 1 is 5, 5 squared is 25, and stopping there. So step 1, okay, you're going to divide 5 into 38. At a first glance, you're like, what? It's not as hard as you think. How many times does it go when you already know 25, right? Oh, I'm sorry, not 5, 25, guys, right, 25. You're going to divide the largest power you have into the number, 25. Would I attempt to divide 125 in? No, that doesn't make sense. So I'm going to divide 25 in. And when I do, it's not really that hard. Of course, it goes only 1 and 1 time. You have to do this the old-fashioned way because you do require the remainder. So 13 is our remainder. Now, what I did was I took our number I recognize that the request is please rewrite this in base 5. I examine the bases powers, and I get a power table 1, 5, and 25. I recognize that this is the largest that will go in. So my first step is take this largest power and divide it into our number and see what I get as a quotient of remainder. The quotient is the first digit of the answer. Okay? Now, the next one, let's get a little bit of a better view. The next one is going to be step 2. It's going to be 5 into our remainder, 13. What do you get? You get 2, remainder 3. You have a 2. The last step is technical, and you don't have to do it. And I'm going to write it in a different color so that you could see that it's really kind of almost never necessary. But I still want to show you the theory. The theory is now, of course, go ahead and divide the last power in, which is 1, right? The last power is 1. What happens when you divide 1 into 3? Don't you get 3? So a lot of students just say, okay, and the remainder then is the thing that goes there. And you could do that. But the logic is you are ultimately dividing every single power, including that 1, into successive remainders. And that's how you get your solution of what the number is in base 5. It's all of the quotients that you get. Like that. Now, this is really not that hard. You just have to practice it, okay, my friends? And I'm going to show you a great number of examples today in class. Before I go on, I'm going to pause here. Does anyone have any questions about this arithmetic or how this came out?
Wait, how did you get the 25?
The 25 is there because we're asked to write this in base 5, right? So, since I'm asked to write 38 in base 5, I have to consider
Thought it
this.
would have been 5 divided by 38.
Well, what you need to do is divide by the highest power you can in order
Okay.
to get it. And that's where your thinking is a little off. That's why it's important to explore all the powers of the base, okay? And you write a list of all of those powers like this. And now you have a power table. Notice that the next power is too big to go in, right? The next power is too big to go in. So you do the highest power you can in. So you first put 25 in. You might be a little confused because I initially put a 5 there by accident. I meant to put the 25. But you're going to divide 25 in. And then with your remainder, now you divide the next successive power, 5 into that. So now 5 goes in. And then with the next remainder, the next power goes in, which is 1 this time. Okay.
Yeah.
Yeah. Okay. And I'm really glad you guys are contributing. Thank you, my friends, for sharing your ideas, because I need you to tell me what you're thinking. I see Lily has her hand up. What's up, Lily?
Now what if you keep doing the dividing, but you come up with like one that doesn't have a remainder, like it divides in evenly?
Oh, you got a good question there. You know what? Let me create one that looks just like that. I'll show you just how to deal with that. I'm really glad you asked that. I never even thought of that. Let's do something like that. I'm going to ask you, okay, to write the number. Let me try to think about this. Okay, all right, I got one. We're going to do, I'd like you to write the number 12 in base 9. And this is going to be a case like you just requested where you wind up with zeros, okay? Please write the number 12 in base 9. Okay, I could do that, no problem. I have to start by considering the powers of 9. Wait, 9? No, base 3. I meant base 3. I'm trying to make it up on the fly, guys. Sorry, in base 3, okay? Write 12 in base 3. So, how do you do that? You begin by examining the powers of 3, right? Okay, let's get a power table of 3 over here. And in my power table of 3, I have 3 to the O is 1, right? 3 to the 1 is 3. 3 to the 2 is 9. And 3 cubed is 27, right? This one's too big, so I'm only going to use these. Okay. Now, if I divide each of these numbers into 12, step 1, put 9 into 12, right? And we discussed that you put the highest base in first. When you put 9 into 12, you get a 1, right? What you have left is 3. So I know there's 3 places. The 3 places will look like this. Let me put it, I'll put it right here. Right? So the first one's a 1. Okay, good. Now for step 2, we'll take this base, which is 3, and divide the next power down into it, which is 3. And what happens? I get 1, and I get a remainder of 0. Okay, so there's a 1 there. Now, when we take the 0, the remainder, and divide the last power 1, and what happens? And now it's theoretical. 1 into 0 is what? 0. It goes 0 times. You have a 0. It's not a remainder. I'm sorry. This is not right. It's just a 0. This is what it would be like if you were missing a place at the end. I'd like to show you also, while we're in this conversation, what it's like if you're missing a place in the middle. Let's say for a minute I was going to ask you to write 17 in base 2. Okay? So if you want to write 17 in base 2, first we have to consider all of the powers of 2, right? So in the power table of 2, let's get that up. And that power table of 2 is going to be 2 to the O, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. Okay? So I listed as many as I could until I've exceeded my number. And notice I'm not going to be using this one now, right? Okay. So how many places should I have? 5. Now, this is the place where what Lily was asking about is what if there's a number missing in between? This is where it's really crucial that you recognize that your answer is going to have 5 places. And you can only do that by examining the power table. There are 5 powers that are below 17. So I'm going to have to use all of them, okay? So there will be 5 places, and my solution will look something like this. It's going to be like that. Okay, now, let's start the work. The first idea is divide the highest power in, right? So for step 1, we're going to do 16 divided into 17, and we get 1, with a remainder of 1. So the first number is 1. I think that makes very much sense to us. That's really very clear. The next couple of numbers are all going to be 0. You'll expect zeros here, here, and here, and I'll show you why. For the next step, you're supposed to take that remainder and make that your dividend and divide in the next thing down, which is 8. We have a very strange question here. How many times is 8 divided into 1? The answer is 0, and there is a remainder of 1. So a 0 goes here. I'm going to pause there so that you can kind of look at that and get that. Because what is step 2? Step 2 is I already did 16. Now I have to do 8. And I have to do 8 into this remainder here. So I'll put 8 into the remainder, and a theoretical idea pops up. What happens? How many times does 8 go into 1? The answer is 0. The remainder is 1. Now let's carry on with the next step. Take my remainder and put the next power down into it. So I did 8. Now I'm going to do 4. How many times does 4 go into 1? 0. So 0 goes here now. Our remainder again is 1. Let's take the next power down, taking our remainder again as our dividend. We're done with 4. Let's try to divide 2 into it. I put 2 into 1. Again, how many times it goes? 0. And what's the remainder? If you can't see it, you would go like this, you know, and you get that 1. So again, our quotient is 0 here. And last, now let's try to divide our last power in, which is the 1. If I put 1 into 1, because that remainder is the new dividend, and 1 is the next power down. 1 into 1 does certainly go 1 times, and this is the answer. So look at how I had 5 steps here, because I had to do 1 step for every single power in the table like that. And now that I did each and every one of them, a couple of times it came up that 0 was the quotient, which is a little bit awkward and strange looking. But when it happens, just keep on trucking, and don't forget that when you divide a big number into a smaller number, you cannot divide it. The answer is 0. If you can't see the remainder is still 1, then go through the motions. 8 times 0 is 0. Subtract, and what do you have? 1. It's a remainder of 1. If you're not sure if this is right, check it. Let's check that number. Well, let's discuss what are the place values of this number, and then we're going to take a short break, my friends, okay? So what are the place values of this number? Well, this is the 2 to the O place. right? This is the 2 to the 1 place. This is the 2 to the 2 place. Ooh, look at what I wrote there. Yeah, that's right. This is the 2 to the 3 place. And this is your 2 to the 4 place. So we have 1, 1. We have no 2s. We have no 4s. We have no 8s. And we have 116. And what do you get? 17. So after you're done going through this hard work here, and as you can see, it's tricky. You might screw it up, right? Check it. Come back and check it. Look, this is supposed to be 1s, 2s, 4s, 8s, 16s. I have 116, nothing else, and 1, 1. 16 and 1 makes 17. So as you get better and better at this, you might be able to look at a number and come up with the answer in your head. This is 17 here because it's 1, 1, no 2s, no 4s, no 8s, and 116. 16 and 1 makes 7. All right. So now you see what it's like when there are zeros in the middle. And also, I just want to mention, this is kind of the hardest part of writing numbers in alternative bases because the division slows people down, and a lot of students really struggle with this kind of division stuff. If you have issues with the division, there's a lot of great videos on YouTube, and also I'm here to help you. I can go through some division with you. But we are going to take a short break because I don't want to overwhelm you with too much math. And when we get together again in 15 minutes, I would like to at least start by talking a little bit about what the Roman numeral stuff is. And of course, we still have a little bit of time to, there's no rush. I just want to make sure everybody really understands in our class. So let's take a little break. And while you're taking this break, I have a great example for you to try out. I'm going to ask you to see if you can figure this question out for me. All right, and we'll be back in just 15 minutes. Right now it's 8:44. My friends, can we please return at 8:59? Okay, and let's take our break, guys. Thank you so much for your close attention to my lesson. I do appreciate it, and I hope you're enjoying it. I sure am. This is one of my favorite topics, and I'd like to see if you can try to figure out the answer to this question. We'll be back at 8:59 a.m. Little break. Okay, there you've got 2 examples. If you want to work on another one, there's a second one. So let's see if we could do those, guys, okay? And we're back, my friends. So we're trying to figure out right now how to convert this binary number, 1011, base 2, into something of base 10. So what we do is we recognize that each of the places is not ones, tens, hundreds, thousands. Instead, it's going to be ones, twos, fours, eights. And that's what's happening here. I put them in first as powers, then I rewrote it using what the actual numbers are. Then I did the multiplications here, and then I added it. The solution is 11 for this question. For this one, we're going to do a similar thing, but we're going to use powers of 4 instead. So it should be 1 times 4 to the O times 4 to the 1, 2 times 4 to the 2, and then, of course, 3 times 4 to the 3. These numbers come straight from this in this direction. 1, 0, 2, and then 3, right? And this number 4 is here because it's the base. And then the powers escalate as you go. So now some basic arithmetic, remembering that anything to the 0 power is 1. So 1 times 1 is going to give that 1. This is 0 times 4, or to give you a 0. This is 2 times 16, and that is 32. And this is 3 times 64, which is obviously 192. Everybody can see that right off the bat, right? I don't know. I'm only human. I probably screwed that up. Hold on. Just check that out. Right? 3 times 64 is 192. I was right. Okay. Anyway, what do we do now? Add them up. So we add them up. We get, right? Oh, wait, did I do that right? No, 225. Okay, 225. So our solution here is 225. Okay. All right. So that's how you would go from a binary number into a base 10 number. We also have some great examples of going in the other direction. Before I go there, though, does anyone have any questions about this one or the other one? All right. So here's another great example. We're going to do this at the beginning of our next class. We're going to do a couple more like that. I have some great cases, and in our next class, we'll do some practice. I'd like to talk a little bit about base 16 because we did ask about that today. If you look here, we have base 16 happening, and since it's 16, we're going to convert these, and they're going to be powers of 16. Let's write the digits just so that we remember. In the case of, after 8 comes 9, but after 9 really comes 10. And if you're in base 16, we're going to use the letter A, right? 11 is going to be represented as B. You can imagine the rest now. It goes up to F. Okay, so, excuse me. These are all the digits. How many digits do you assume there will be in base 16? There will be 16 digits, and the digits are 0 through 9, and then A, B, C, D, E, and F, and that's a total of 16 symbols that can be used. Now, if you're trying to convert this 16 base number into a decimal number, we have to take each of these and use the powers of 16. So let's consider the powers of 16 table now. What is the power table of 16? Well, of course, 16 to the O is 1. 16 to the first is 16. 16 squared is 256, right? We're going to use that as a reference right now. So this is 4 times 16 to the O. This is E times 16 to the 1. And this is B times 16 to the 2. That means 4 times 1. This means E, which is 14. And this means B, which is 11. And 16 squared in my power table is 256. Okay, now I have to multiply these all out. This, this, and this. I think I can handle 4 times 1, right? Then I need 14 times 16. Then I need 11 times 256. Then I got to add them all up. So this number is equal to 3,044. There's your answer. So now you see what it's like to convert numbers that are in base 16 into our decimal number. We also will explore what it means to change back in the opposite direction, given a decimal number, come back into a hexadecimal number. Okay, and that's a great example. When we get together next time, we'll do some more cases of this. And then we also can talk about how to convert into another base, like 37, and some other numbers, and we'll do those later. But I think what I'd like to do with you guys now is talk a little bit about Roman numerals before we carry on, and be familiar with that before we end our lesson, because I have 10 more minutes with you. And in your web assignment, there are a decent amount of questions about Roman numerals. So I want to start by sharing that with you. Let's take a look at a little PowerPoint that I had made here. Okay, so what you're looking at is a manipulative that I used when I taught a class for HESI. HESI is H-E-S-I, and it's the exam that the nurses have to take. It's called the HESI exam, and I worked with the continuing education department at Rowan College and taught that for a little while. And when I did in the HESI, they have them do things with military hours. They have them do conversions with CCs and things like that for medications, and they also make them understand Roman numerals for different reasons. So here's what I have for Roman numerals. You could look this up on the internet. These things are all, you just Google them. This is something out of Google Images just to make it funny. Caesar is saying, "Hey soldier, what time is it?" And then the soldier is trying to say 9 to 9, which is kind of a silly idea. But anyway, when you see a smaller number before the number, you're supposed to subtract. And when you see a larger number and then a smaller number, you're supposed to add. And it might be a little tricky, so I have a couple of great examples of that. And as you can see, they do exist all throughout architecture and literature. You're looking at some really amazing, interesting things we have right here. This is the New York Library in New York City. This is the Statue of Liberty, of course. And we have other really great examples of Roman numerals that you might see in art and in architecture. So here are some great examples for you guys to try. I'll leave those up, and we can look at those tomorrow a little bit. But what I'd like to show you is basically what each number means and how to do them. So let's start with these, and then next time we get together, we'll do some more advanced ones. Okay. Our first example is MCMLXXI. The easiest way to try to figure this out is to go left to right and ask, am I increasing or am I decreasing? So from 1,000 to 100, am I increasing or am I decreasing? This is 1,000 and this is 100. It's a decreasing, so I'm not going to do any subtraction. I'm going to just write down that I know that this right here represents 1,000. That's the beginning. Excuse me. Next, from C to M, am I increasing or decreasing? From 100 to 1,000, I'm increasing. So since I'm increasing, I have to subtract. I have to subtract 100 and 1,000, and it gives me 900. From M to L, meaning from 1,000 to 50, you'll notice I'm decreasing. Since I'm decreasing, I'm not going to subtract, and I'm going to just use it the way it is. It's 50. From 50 to 10, I'm also decreasing, so I won't be subtracting. That's a 10. If it's the same thing, you just write it again. And now from 10 to 1, I'm decreasing, so I will not be subtracting, so I have a 1. This is probably the easiest way to figure out Roman numerals. You only subtract in the very specific case where you see two letters that show an increase as you're going through. Okay? Now, we'll add these numbers up, and it looks like I have 1971. And 1971 is a year that is not that far away from where we are on the time span here. So you might see some buildings that have this. There is a building in Williamstown that was made in 1905 or 1904, and it has the Roman numerals on it. I'll take a picture of it next time I'm driving through there and share it with you guys. But you'll see things like that on there. All right, so let's do another one. I'm going to ask you to try just one more. Everybody try to figure out what that year is for the Statue of Liberty. And it's hard to see it, so I'll write it again for us. Okay, the number is MDCCL. XXVI.
Wait, what's D?
D is 500. 500.
Okay.
Okay. So we only have about 5 more minutes to class. I'm going to ask you to work on this question. I'll show you the answer in just a minute or two. And in the meanwhile, I'm going to take attendance for us so we can all get credit for being here. Okay, guys, let's take a look at the answer to this question, and then we are going to dismiss for the day. I did take attendance. Thank you for your patience with that. Let's start by going in this direction and asking, when does it happen that we decrease? That's when we need to subtract. I mean, when we increase. We need to subtract when we see an increase. So we're going from 1,000 to 500. That is a downward, so this is going to be 1,000. We have from 500 into a 100, so that is going to be a downward again, so that is 500. And then we have two that are equal, so I'm going to put them both. Then I have, again, from 100 to 50, I have a downward, so that is, again, just what you see there is 50. In fact, in this one, they all go down, don't they? There's no subtracting, which makes it a little easier. So the tens both are used. And then, of course, 5 and then 1. What's the number? 1,776. Surprise! The Roman numeral on the Statue of Liberty is 1776. But you already knew that, didn't you? Haha, yeah, I knew that too. Okay. Anyway. My friends, that is all I have for you. And thank you for coming to class today. Once again, Tuesday. Your exam is still a couple weeks out. It's going to be, I think, 2 weeks from today is what our calendar says. Take a look at the syllabus and confirm that. I have it right here. Let's look at it. There you go. So where are we? Let's see. Where are we? Well, we're looking at exam number 2, going to be October the 8th. So we have Tuesday and Thursday next week for instruction. Then the following Tuesday will be our essay day, and then we'll have our exam on the 8th. Okay, so that's all I have for you, and thank you so much for your close attention. We are formally dismissed now. If anyone has any questions, now's a good time to ask. Thanks for your attention, guys. Have a great day. I see Cecilia, Cheyenne. Do either of you have any other questions you'd like to ask Cecilia, Cheyenne? Is there anything else you'd like to talk about? We're going to dismiss and close the classroom now. Well, thank you so much for your attention, guys. Have a great day.